Welcome to the frontier of cutting-edge technology, where innovation isn't just a buzzword, but a living, breathing marvel. Picture this. Nestled in the heart of Granada, Spain, there's a workshop buzzing with excitement, where engineers are turning dreams into reality. And at the center of it all stands a true game changer, the iron engine, an icon of innovation. But what makes this creation so special? Well, let me break it down for you. Imagine an engine so compact that it could fit snugly into your palm, yet packs a punch that puts giants to shame. We're talking about the iron engine, boasting a jaw-dropping 120 horsepower while barely tipping the scales at 35 kilograms. It's like having a racehorse in the body of a greyhound, sleek, powerful, and ready to conquer any challenge. Now here's where things get really interesting. Forget everything you thought you knew about engine design, because the iron engine throws the rulebook out the window. Instead of your typical cylinders and crankshafts, this marvel employs a revolutionary approach. 8 horizontally opposed pistons dancing in perfect harmony. But wait, there's more. Picture a landscape of undulating waves, like the rolling hills of Granada itself. Now imagine those pistons resting on rollers, navigating this terrain with precision. When the magic of combustion kicks in, it's like a symphony of power, propelling those pistons and driving the rollers down those wavy slopes. And here's the kicker. These rollers aren't just along for the ride. They're connected to twin undulating components via a common shaft. So while each piston does its own thing, all that force comes together in a synchronized dance, producing a torque output that's nothing short of mesmerizing. So there you have it, the iron engine, a masterpiece of engineering ingenuity that's rewriting the rules of the game. From its humble beginnings in Granada to its roaring success on the track, this is one innovation that's truly in a league of its own. Buckle up, because the future of technology just got a whole lot more exciting. This architecture holds the tantalizing possibility of connecting drivetrains at either end, paving the way for a simplified, well-balanced, and lightweight four-wheel drive system. The absence of conventional components like cylinder heads, cams, and valves negates the need for a cam belt or chain, streamlining both the engine's design and its maintenance requirements. So how does this engine achieve intake and exhaust without the traditional valves? Its operation echoes that of conventional two-stroke engines. Intake and exhaust ports exist in that the pistons themselves open and close as they move. Nestled between the pistons at the engine's heart are a fuel injector and a spark plug. The spark plug initiates the combustion of the air-fuel mixture, generating pressure that propels the pistons outward. As they move, the pistons unveil the intake and exhaust ports. Half of the pistons are dedicated to handling intake, while the remaining half manage the exhaust. To address the problem of exhaust gases contaminating the intake, the in-engine employs a scavenging process akin to traditional engine designs. Initially, the exhaust port is exposed, allowing high-pressure exhaust gases to vacate the combustion chamber. This rapid exit generates a low-pressure vacuum that sucks in fresh air from the intake chamber, creating a clean environment for the next combustion cycle. Then, as the exhaust mechanism rotates, it pushes the pistons upward to seal off the intake and exhaust ports. Fuel is then injected, and the chamber is compressed, setting the stage for the next combustion cycle. This inventive engine lacks the cams and valves found in traditional systems, but features the advantages of direct injection, sidestepping the common issue of intake valve deposits usually associated with this technology. However, a point of potential confusion is the engine's nomenclature as a single-stroke or one-stroke engine. In truth, it operates on a two-stroke cycle. The first stroke sees the combustion and exhaust processes occurring almost concurrently, while the second stroke encompasses the intake and compression phases. Labeling it as a one-stroke engine would be misleading. There are no successfully mass-produced one-stroke engines, and with the current state of technology, it's improbable that we'll see one anytime soon. Another innovative feature of the in-engine is its capacity to adjust the compression ratio effortlessly. The engine's dual wavy components, while connected, aren't rigidly affixed in their relative positions. Instead, they sit within angled grooves that allow for positional adjustments. For instance, Aligning both pistons at their top dead center, while the waving components are in a particular configuration, allows the engine to achieve its peak compression ratio, such as 12:1. Conversely, adjusting one wavy component while keeping its opposed piston at the top dead center changes the position of the other piston slightly, reducing the compression ratio to say 9:1. The potential integration of a turbocharger makes this feature even more compelling. At higher RPMs, the engine could opt for a lower compression setting while boosting turbocharger output for robust power delivery. In contrast, at lower RPMs, it could maintain a higher compression ratio for greater efficiency and responsiveness without relying on turbo boost. Essentially, the engine reaps the benefits of both low and high compression scenarios through a brilliantly simple mechanical design. But the merits of the in-engine extend even further. One of its standout attributes is the impeccable balance it achieves, both primary and secondary. The opposed piston configuration neutralizes the forces exerted by each piston pair, leading to remarkably smooth operation. Moreover, the absence of a connecting rod means the engine attains a flawless secondary balance as well. This fusion of innovative features and engineering excellence makes the in-engine a standout candidate in the quest for automotive efficiency and performance. One question that often arises is if the in-engine offers such groundbreaking features like problem-free direct injection, adjustable compression, and unparalleled balance, why hasn't it swept the automotive world off its feet? The notion of, if it's so great, why isn't it everywhere, is flawed because it underestimates the inertia of established technologies. The rod and piston engine design has enjoyed over a century of rigorous research, development, and optimization, making it a formidable incumbent. Imagine for a moment if history had unfolded differently. What if alternative designs like the Scotch yoke or the in-engine had been the focus of a century's worth of innovation, while the rod and piston approach was the newcomer? We'd likely be questioning why such a brilliant rod and piston design wasn't more prevalent. The tides, however, are turning. The rise of electric vehicles is nudging the automotive sector to explore other avenues of propulsion and energy. While electric cars may outperform internal combustion engines on various fronts like torque and efficiency, obstacles such as charging infrastructure and battery longevity create an opportunity for novel internal combustion engines like the in-engine to make their mark. This potential is further underscored by the engine's successful integration and testing in a Mazda MX-5. That said, it's crucial to consider the engine's drawbacks and challenges. Although compact and lightweight, the in-engine's long-term durability remains an open question. The intricate, wavy components and rollers must withstand high pressures and temperatures over extended use.